Hey students, I hope that your long weekend has been going well, and I wanted to introduce acids and bases using our videos, and I'm planning on trying to get our videos back online and producing a little bit more. It's just hard with all of the letters of recommendation that I've been writing and all the lesson planning that I'm doing, but without further ado, let's get started. Here's our new unit, acids and bases. I'm super excited, and equilibrium is going to be playing a big role in it. Here I have written a few examples of acids and bases. Strong acids you might have worked with. HCl, we've definitely worked with that before. Acetic acid, a lot of you are recognizing that that is from vinegar. Ammonium. Here we have NaOH. We've definitely worked with that before, and KOH. Ammonia, that is a weak base, and the acetate ion. A lot of you noticing, well, hey, the acetate ion is just a acetic acid without the hydrogen. Yeah, totally. Okay. A lot of you smart folk, a lot of you really witty people are noticing that, hey, a common theme on these acids is that they all have an H attached to them, or an extra H, such as ammonium. And a lot of you are saying, well, maybe what makes an acid is having a hydrogen. And I would say that you are close, according to the Bronsted-Lowry definition of acids and bases. This is a scientist who researched acids and bases extensively, and he came up with the definition that acids are proton donors, or H plus donors. A lot of you are like, wait, that's not a proton. Well, technically, hydrogen is made of one proton and one electron, and if you take away that electron or make it a positive ion, all you have is a proton left. Okay, so a proton donor. And Bronsted-Lowry bases, well, you might be wondering what are the similarities here, and we'll talk a little bit more in definition in detail about what it is, but for now just know that Bronsted-Lowry, that's not a B, but it's a really bad B. Bronsted-Lowry bases are H plus acceptors. Let's look a little bit more in depth into how these donate protons, how they accept protons. There's a few things I want to emphasize, and before we really get started in class tomorrow. Okay, so again, Bronsted-Lowry acids are proton donors, and bases are proton acceptors. Let's look at the acids first, because they tend to be a little bit more simpler. Tend to be simpler than the bases. Here we have the strong acid, hydrochloric acid, and the weak acid, acetic acid. Hydrochloric acid, well, if you were to put this in aqueous solution, okay, what you would find is that it will donate a hydrogen, okay, and a chlorine ion. Now there are two things that people are starting to notice. Well, three things. Here's the first one. Hey, okay, I see it's an acid, so that's the first one. I see it's an acid. It's donating the proton. Okay. Second thing, a lot of people are saying, hey, I totally see that if this is an acid, can't this accept a proton? So won't this be a base, right? Because can't that bond with that to form that? And I'll say, yeah, you're completely right. This is the acid, and what we like to call this is the conjugate base. The conjugate base. It's the conjugate base to this acid. Okay. And the third thing a lot of people are noticing is, hey, there's equilibrium. Oh my gosh. So if we had a K, then we would write the K expression to be concentration of H plus times the concentration of Cl minus over the concentration of HCl. Oh, no way. Right, and since these are all aqueous, then we can write it. We don't have water, or none of them are solids, okay? Now, if I said that This is the strong acid, this is the conjugate base, okay? What I mean by a strong acid is that this is a stronger acid than this is a base. This is more likely to dissociate than this will take up, okay? This, and what we mean by strong or weak is their ability to dissociate, their ability to break up into ions and react with things, okay? And in this case, HCl is a strong acid, meaning that we expect it to dissociate quite readily, or really fast. And this K, or what we like to call Ka for acid, would be quite large. Okay, this would be a large Ka. Okay, the top here will be much larger than the bottom at equilibrium. Let's look at a weak acid. When we look at a weak acid, well, the same thing happens here. We know that it donates a proton. Here is, and it's important to note that usually the proton that we donate in our chemical formula is the one at the end, not something in between. Okay, usually they're emphasized. Here, acid, conjugate base, this is our proton donation. If we wrote our Ka for it, okay, we would expect this Ka to be relatively small. This would be a small Ka, meaning that acetic acid will not really dissolve if we put it into, not dissolve, it won't dissociate very well in the solution. If you put this in solution, most of it will stay like this. Only some of it, a very small percentage, will actually dissociate. Because the Ka is pretty small, meaning that this is emphasized and these are not. Okay? So those are acids and bases. Let's move on to, those are acids, let's move on to bases, and bases are a little bit more complicated than that, but not too much more complicated. Here, we have a strong base, NaOH, it breaks up into Na, oh, that's a weird Na, and A plus ions plus OH minus ions, and you're probably wondering, wait a minute, in our original definition of acids and bases, we said bases are proton acceptors. Well, what do we know here that can accept a proton, a H plus ion? And if you said OH minus, you're completely correct. H plus bonds with OH minus to form water. Okay? Now a lot of you are noticing again, hey, wait a minute, this is at equilibrium, meaning that we can use our equilibrium expression, and last time you used A for acids, so what do you think we're using here? And you said B, yes, you're completely correct, Kb for bases equals the concentration of I keep doing that, Na times the concentration of OH minus over concentration of NaOH, and just like for acids, we can say that this is a strong base in that it dissociates into its ions very readily, very well, very fast. It happens, well, not fast, but it happens to a great magnitude. This Kb, large Kb. This would be a large Kb. Okay. For weak base, now a lot of people are wondering, wait a minute, where is the OH that can come off to react with hydrogen? Well, and this is where bases get a little bit tricky. Okay, NH3 is in itself a proton acceptor. Okay, it doesn't release an OH to accept protons. It in itself is a proton acceptor. Okay, and it also does produce an OH minus. So here we go. NH3, whoops, messed up there. NH3 will react with water. Okay, let me put in aqueous solution, of course. And I keep forgetting my my states of matter here. What am I doing? Okay, here aqueous solution. It reacts with water. Okay, And what it's going to do is going to take a proton from that water. It'd be NH4 plus OH minus. Okay. And a lot of people are saying, okay, here's our KB expression. NH4 plus times OH minus over NH3, and you're recognizing that water is not included in our KB expression, okay? Because the amount of water does not change in solution. And a lot of people are saying, hey, wait a minute. This takes up a proton and is creating an OH that can take up another proton. So wouldn't this be a strong base? Well, again, let me restate that a base and acid are really, their strength is really dictated by the how much they can dissociate in solution. Okay, this doesn't happen nearly as much as this will happen. This doesn't happen nearly as much as this would happen. This KB is actually very small. Small KB, okay? This, when you put ammonia in solution, most likely it will stay as ammonia and it won't form ammonium or OH minus, okay? Now, for the length of this video, I'm gonna try to end pretty quick here. Water is an interesting molecule, and we're going to be working with it a lot actually throughout this unit. Water here can actually dissociate to form H plus and OH minus, and here's aqueous. Here's aqueous, and we don't say aqueous for water because that's just the liquid here. Okay. And if we write the K expression, I'm just going to KW for water. This is equal then to the concentration of H plus times the concentration of OH minus, and at 25 degrees Celsius, just by nature, the KW would be 1 times 10 to the negative 14. Okay, just by nature, this is 1 times 10 to the negative 14. Interesting. Okay, so this tells us that this doesn't happen very often. Most of these states is water, but it does happen. Okay. And they come out equally. My question to you is, what is the concentration of protons in solution with pure water? And my second question to you is, would you consider water as an acid or a base? I don't know. See you guys in class.